spoken, the first one of the spring semester. So today's speaker is Roger Key. Roger Key. Brief academic summary. So Roger got his undergrad degree at at Oklahoma State University, so Cowboy. His MS at Kansas State, Wildcats. And now he's with the Bulldogs at Fresno State. He's also been a faculty member at FCC since about 2000 or even before. So the Rams.
Rams.
And he's been a member of AAPT since 1989. Has held several leadership roles in that regard. And today he's going to basically tell us a bunch of new labs, demos, and cool stuff that he's basically put together over the pandemic, and that he wants you guys to know about and use as we move forward into the new in-person format. Anyway, so Roger,
thank you. Okay, so the things that I'm not doing a standard demo show today. This is more like tools that we have acquired during the pandemic that you're probably not aware of, that you might like to use in your classes, whether it's in person or virtual. Some of this stuff is good for virtual. I'm going to start with a demonstration that's old and famous, but difficult to show a large class. Right over here, you got a silver can and a black can. If you've ever driven the black car in Fresno in the summer, you know where this is going. You shine a light on here, and then this one heats up faster than that one. But how do you show this to a big class? Well, now you can. You see these little things here? Wireless temperature probes that go to the Bluetooth on the computer. So right now they're both at the same temperature, right? Pretty close? Pretty darn close. I'm going to plug this in. And if the light doesn't bother you, you're sitting in the wrong place. Sorry.
So we'll know which one's which right away, huh?
Yeah, so, can you?
Well, not yet. There we go.
Well, okay.
Well, maybe not.
The black and silver, they're going to take some time to change. So I'm just going to leave that alone. We'll come back to it. Okay, now, another favorite demonstration. Oh, and I tested this. This is really cool. Oh, by the way, since I did start the light, let me start taking data. And then we'll be able to see the graph of the temperature changing later.
It's number 2.
But we only have one line. Oh, they're really close together. All right, so now, another demonstration that is easy to do on paper, but difficult to do in person. How do you prove to students that Newton's third law is true? That an action force and a reaction force are equal but opposite in direction? Well, we just got these. Let me turn these on. And I can adjust it on the computer. I have to connect to the two carts to make changes with Pascal Capstone software. We should be good at this range. I had to move these sensors over because they were too far away. Okay, so now I go here. Again, this is wireless. Through the Bluetooth, there's the red card. Takes a moment. Takes another moment. Yeah, okay. This went faster earlier. Okay, there it is. And there's the blue card. Failed. Okay. Let's try again. Let me bring it over here.
Yeah, how far away wireless have you found that works?
Actually, Ray Hall has done this in a slightly different form, kind of in this
Okay, is that why you
configuration. That's why I thought it would work here. All right, so now we've got this vector display. Still connecting. Is this on? Yes, it's on. Okay, there we go. And we'll go to the Smart Cart vector display, both red and blue. And we have several options here. The carts are amazing. They've got all kinds of internal sensors, similar to what you'll see with the phones next week. This has an internal 3-axis accelerometer. It's got a force sensor over here. And it's also got, what do you call them, rotary motion sensors? You remember the old-fashioned mouse? When you move the mouse ball, it would turn 2 little wheels inside. That's what those are. So, and then, yeah, the force sensor I mentioned. Okay. So now I'm going to set this one for velocity, and this one for velocity. And you see the blue one's pointing the wrong direction, so I need to reverse that. Pardon?
So those flashing arrows will show us that.
Yeah, so you see up here, I just clicked the little box change sign for the blue card. So now if I push it, you can see the velocity
Yeah.
as a vector. And if they move together,
One way, green the other.
pardon?
It looks like it goes red one way and green the other way.
Oh, yeah, but I can't change the color.
No, well, that's kind of cool though.
But I
Like,
can make
we call
a
like a
point.
red direction or
Yeah.
green direction.
Okay,
Yeah, I like that.
so velocity is very fine. Let's look at force. Okay. Down here, and the cart actually has a force sensor built into one end of it. There, and I got blue for change sign again. And you know, when they collide, they push against each other. Right, you can see the harder I push, the more arrows you get.
That's very cool. I
Yeah.
like that.
And then if you have a collision, you can see where the forces are. Pretty cool, right?
Yeah.
Okay, now when you start talking about Newton's second law, you know that the force and the acceleration are closely tied together. So we can look at acceleration on one and force on the other. You see it only accelerates when it's changing speed. No, this is not flashy, but it's cool. If you teach.
Now, Roger, can you add masses, I guess, to each car too?
Yes, you can. There's still space back there to add mass on gauge one.
And that can definitely change.
Okay, now, it's been using the wheels as the sensors. It's also got that internal 3-axis accelerometer, pardon me. And that's what this one is down here. What was that, the red car? So even without the wheels turning, it will sense the acceleration due to gravity. Right here in the rear. Is it reversed? Pointing the wrong way. Oh, did I didn't change this one. This one's still on force.
So, Roger, it looks like, yeah, you have two directions, a green direction and a red direction.
Yeah.
Right, I think that's kind of, as long as you.
That's reverse pulse.
I like that. But you gotta, I agree, you gotta get it right way.
There. That better? Is it pointing in the right direction?
Yeah, green.
I can't see it. All right, so that's cool. And force, acceleration, velocity. Acceleration in two forms. One's from the wheels and one's from the acceleration sensor inside. By the way, interrupt me anytime if you have a question or you want something you want to test.
Question, do they have on and off switches on each car?
The car controls the arrows. And to turn the arrows off, you just unplug them. Yeah, I just turned the cars off. So that's going to complain in a second. Let's check our temperature probe.
Oh, yeah.
Okay. What I think was really interesting about this is two different brands. They both sell their own little Bluetooth dongles, and they insist that you buy their dongle to work with their equipment. But our new laptops has built-in Bluetooth, and it works already. You don't need those dongles. Okay. Another old favorite, but previously, this would have a little trigger sticking up off the side of the track, and it would have to pass through perfectly straight in order to work. This has an internal timer. So let me turn it on, and when I press this little button here, some time will go by, and then it will launch the ball. And it catches the ball. Most of the time. Most of the time. I should have brought an extra ball back. Okay, thanks. Okay, so now, instead of having to get everything lined up, so you still have to make it straight, you can give it a little push. There.
Yeah.
And a little bit faster. Oh, it's out the door.
See, that's why you put it in your head, man. Yeah, that one you say, that's good. Oh, that's good.
Okay, so we got a lot of smart people in the room right now. Let's see if you can answer this one. What if I do this?
Oh, it's gonna accelerate
Now it's going to accelerate down the track. If if I launch the ball
They're
now,
both accelerated.
is it still gonna catch it?
Yeah, it should, they're both accelerated.
No. I hear no, I hear yes. Well, how do scientists figure these things out?
Well, yeah, you know, do it.
You're doing experiments. Sorry, go ahead.
Both accelerated downhill.
Doesn't have a little vector forward now that you've got the track slanted, is that gonna?
Yeah, it's taking the velocity vector of the launch and tilting it a little bit like that.
But the ball isn't going to accelerate in the horizontal direction. It'll be moving in constant speed in the horizontal
Good
direction.
point. Good point.
Neither is the cars.
The car's accelerating, but the ball isn't in the horizontal direction. So the car will outpace the ball.
We got some legitimate argument going on. You want to find out?
Well, it might not, yeah.
Yeah.
That was real slow. Let's go a little bit faster.
That's what I wanted.
Still caught it. Still caught it in the same place too. So,
Let's go for a bigger acceleration, prop that thing up. That angle might affect you a little bit the way the car is now.
Let's put some money on this one too.
I can put it on the track before it lands there. Ready? Maybe another day.
Off McLean. No.
It's a couple $100. I don't want to break it right away. Okay. So that's like the mechanics kind of things that I had out here. Right? Oh, no, right here. This is in addition to the lab equipment. Also, we have a set of this for demo. And we have aluminum meter sticks now. And this has a bearing pivot and a little bubble level built into it. And just right in the center. It's got a little indicator here. I'm not being real careful because I'm brushing a bit there. So that's like right in the center. And you guys remember taking the wooden meter sticks and balancing them on a nail? That kind of thing? There you go. And then we have these that slide on.
The hang thing.
And hang things on. Right? So you can do a meter stick balance in the classroom if you want to. Okay, I won't do it.
I can't jump here, is that pretty sturdy? I mean,
Oh, yeah.
is that a pretty sturdy thing there?
The only thing I think might be breakable is this has a notch in the axle, and this has a little plastic raised part
Okay,
that has to go on the notch. It might be tempting to just force it on.
Okay.
Okay, so that's that. And while I'm using this device, I'd like to move on to waves and sound. Okay, now. Oh. Where did I put the thing with the level on?
On that table.
Here?
Yes.
Oh, there it is. Okay. So I'm going to use this as a pivot for a physical pendulum. And very gently get that on there. See, that's what I mean. It's tempting to just push it on, but it's got to be in just the right place. There. Now I'm going to raise this up. All right, so now I have a physical pendulum with a gadget on the bottom. And that gadget is shaped like a bat. Can you tell? Because it's giving off about a 40 kilohertz audio signal, which you can't hear. Or it will be when I turn it on. It's on now. Can you hear it? You can't hear it. Okay. So I'm going to get my bat detector here. Here's my bat detector, and it's going to take that 40 kilohertz sound and turn it into something you can hear. Let me stop that. And it's doing it again, I can tell. I had a problem with this earlier. It was backwards. It's the Doppler effect. But it's the Doppler effect at 40 kilohertz. And this just translates the sound into something that you can hear. Now, you know that when the Doppler effect is going on, if it's moving towards you, it should go up. And moving away, it should go down. There's a Doppler effect at a very low velocity. Now, how can that happen at such a low velocity? It's this right here. Because if you want to hear the Doppler effect, the shift in the frequency, you either have to move fast or get a high frequency. And with this, you got a really high frequency, so you don't have to move very fast to hear that.
So you make it inaudible to audible.
Yeah. Isn't that great? It's not the Doppler bulb on. So,
You know, you can do a lot with that, Roger, too. I see that bad idea. You know me and outreach, man. I got
oh yeah.
Oh, yeah.
I did not do this myself. This was invented by my counterpart at Yale University. And we see each other at meetings all the time.
Right.
And he was selling this as a kit. So I bought the kit and put it together. Okay. Well, not my idea, his idea. I just put the kit together. Okay, so talking about waves and sound, let me get this out of the way. And we have a new wave generator right here. Pull this out. It's really difficult to see with a yellow string on a white background, right? What if I turn the lights off? This might be easier. Let's find out.
You see the yellow on the cells, that's working.
I'm going to turn the projector off temporarily. Take a minute to warm up again. And come back to it. Oh, you know what?
Now, did you say new frequency generator? That looks like an
Uh,
old audio oscillator thing.
This is the old audio oscillator,
New when you
but can you see the wave on the string now?
Oh, yeah. Oh, now I see that. Yeah, I see it now.
And you don't hear anything. No, you're not supposed to hear anything. You know we have that jigsaw that we bring out
Right, right,
to
right.
make a wave. It's really noisy. And even the other one had a problem. You remember the one that oscillates up and down? It had a problem that the string would fall out of it. And now we have this. Still kind of hard to see, right? Okay, now if you're sensitive to flashing lights, you might want to close your eyes for a moment.
Cool.
Now we have a strobe. And you can adjust the frequency of the strobe to match the frequency of the oscillation, make it a little bit better. And it looks like it's standing still or moving. Kind of hard to match exactly. It has a coarse and fine adjustment. I'm moving the fine adjustment right now. But we've never had a decent strobe. We had a strobe light, but it was never anything this good. So now we have a four-source, digitally controlled strobe light. You can visualize it. Another way to use this is to have a fan spinning, and you can measure the speed of the fan. Anything that spins, you can measure the speed.
So Roger, you tell me that strobe, that we can technically hook it up electronically to anything, is that what you're saying?
Well, you have to be able to plug it in.
Okay, but that's
It's not battery powered.
Okay,
But as long as you can plug it in, you can shine these strobes on anything.
okay. But I mean, as far as adjusting the frequency to match something, because you were, I mean, how are you adjusting the strobe frequency?
Coarse and fine
Is
frequency
it a
adjustments.
digital readout, or?
Yeah, it's got a digital readout.
Okay,
And you can actually hold that one and move to another one and come back to it.
okay.
Yeah, it's interesting that way. I'm still learning how to use it. Okay, so that's the beginning of the waves. Another old favorite with the waves are the beats. These are new. They have these weights that you can adjust up and down here. You tell me if you can sense the difference between these two tones. There's a difference in timbre, but not really much of a difference in frequency, right? Very slow beat, can you hear it? Okay. Let me adjust this mass. And do it again. Too much. Adjusted it too much. There, that's better. Now you can hear the beat, yes. That's right. Now you can hear the beats. Now, if you can get this tuned really well, which I failed at right before this meeting, you can take a ping pong ball on a string. Maybe you've seen this before? Okay, if you get these tuned really well at the same frequency together, you can put the ping pong ball up against this one and strike this one. And it'll cause that to vibrate. And then the ping pong ball goes crazy like this. Okay, maybe it doesn't. I think there's the tape and there's string there getting in the way. There you go.
Yeah. Because it'll kind of oscillate at a regular frequency, doesn't it, Roger? It kind of bounces like that. I've seen you do it before.
Yeah, I've done it before, but I just couldn't get it tuned this time. Okay?
Hot glue next time for ball?
Say again?
Hot glue next time?
Yeah, so there's no tape. Hot glue might be better. Good suggestion, thank you. Okay, so we've done that, we've done that, we've done that. Don't have anything else hiding over there? Good, okay. How are we doing on time?
Good. Hey, you didn't happen to bring,
Little bit.
you showed a few of us a device that you had that you were showing us a magnetic, electromagnetic effect swinging through as a pendulum.
Right over there.
You do have it.
That's
Oh, I
coming
see
up.
it. Okay, good.
That's coming up.
No spoilers.
Okay. Well, why don't we do it now then?
Let's do it now.
Let's do it now.
This is pretty cool.
Oh, and we actually have a good big magnet.
That's what I was saying, yeah. Bring that on.
Many of you have already seen this one, right? And Dr. Zhang brought his magnetometer down here, and we actually measured the strength, it's written on here. That's stronger than this. Creates a stronger magnetic field between the poles.
We wondered that when we were playing with it. It
Yeah.
turned out that was.
Okay, so this has several things you can do with it. It's two very strong magnets set on these things that you can tighten and loosen to get them closer or farther together or farther apart. And I'm just going to set this in here. I've got it kind of tilted so you can see what's happening. I've got it on a support, and this is swinging between the poles of the magnet. Boom. The eddy currents create a magnetic field that opposes the original, and that thing
Look
just
how
stops.
smooth that is. That's so smooth.
Very smooth, okay? Now, what about this one? Okay, this was the first one I did. This one has slices in it. Any predictions? Same thing?
It's gonna go through, but it'll slow down, but
Goes through pretty good, pretty
That
well.
didn't really act like
I
it
thought it would
stopped.
slow
those
down a
guys.
little bit.
Mhm. Okay, so to make Paul happy.
It's like
You
eliminations
got
on
another one. Look at this
Facebook.
one now. What do you
Yeah,
think that
yeah.
one? Okay, look at that one.
Oh.
That's closed up.
Complete,
Ah, okay. So this is a combination of the first two. Put that in here.
Isn't that cool?
All kinds of discussion can be generated here. Now, this next step's going to take a minute or so setting up, changing modes now for this device. We've got a wire that is suspended from, get that untwisted. That, and the idea is that you set the magnet like this, and you lower this down. They made the tolerances really tight on this, until the wire is in between the poles of the magnet without touching them. And it's a copper wire, so it's not ferromagnetic, it's not direct. And I'm still touching it. There. We want this to be able to swing freely. And all I have here, you know, in the past we've done this with big beefy batteries, power supplies. This is just a double A. It works with a double A.
There you go. So the big switch we have.
Its initial motion is away from me in this polarity, and if I turn the battery over, its initial deflection is towards me. There. But you don't need the big, heavy power supplies and battery anymore for this kind of demonstration. Now, you might say it's a little small for a big classroom.
Well, you let them come up and try it now. Before
Let them come up and
we
try it,
let
sure,
them touch
because there's
it.
nothing dangerous. Okay, so you might say, and you would be right, it's a bit difficult to see. So I want to show you some options we have now, besides this document camera that they put in the classroom here for us. You can see, it's a decent doc cam. But the wire's so short, and it's bulky, it's hard to move around, difficult to use. So I've got this doc cam, now, and you cannot use this one in Zoom. But this one you can. Since it's in your computer, you can put it on Zoom, right? But it's a little bit laggy to the video. See that? Great for static images, not so great for things that might be moving. But you could also take it over here and put it on something like this. Okay. How's that? I would take time to adjust it, but you can see it's not bad. It's not bad in that application. Okay, so enough of this one. Let's move on to the next one.
Hey Roger,
Yes.
related to the cameras and visualizing the experiments on the screen, do you know of any sort of video software that will, for example, if you're doing the cart with the projectile, that'll take like 10 images and stack them on each other to show the ball in motion?
You can do.
Kind of like the days of old when you had the strobe and then you take photos at the same time to do that.
Sorry, the HDMI cable came up. Actually, if you have Pasco Capstone, it has that ability. It has image capture,
Okay.
and then it'll let you analyze the motion. We don't use it, but it's there. Okay. Yeah, I know it's already ready. There. How's our temperatures doing over here? Still getting hotter. It's warmer up here. Okay, and now we have another document camera that gets its power from USB, but it has to plug in the HDMI. So this one, since it goes straight into HDMI, it's actually not too bad with motion.
That's real good. Yes.
On the other hand, you can't use this with Zoom. Okay. Well,
Maybe you can adjust frames per second for the other one.
pardon?
Adjust frames per second for the other one?
Perhaps. I'm just plugging them in and using them. So maybe that is a valid point. Okay? So you're welcome to come try any of these, borrow them, whatever. Look, what happened with that. Okay. Now, that's the document camera comparison. Let's look at a USB microscope. I got this thinking it would be good for looking at, and we have used it for looking at the interference fringes from double slit interference, the laser. Those squares are 1 centimeter. Oh no, 2 squares make 1 centimeter. See that? Oh, you can't see the leaves. There. Well, anyway, 2 of those squares basically make a centimeter.
Does it have different power or just one power?
Just one power. Just one power. Now, whoops, it's got a little suction cup that's real easy to pop loose, but you basically screw it down and snap it again. There you go. Now the light is dimmable. I can dim the built-in light, and I can actually snap a photo. Dr. Ringwald was kind enough to donate these, was it yesterday?
Yes.
Yeah. And little rock samples that I thought might be nice to put under this microscope. Take a look at. And this one you have to manually focus. But it's pretty neat. I'm going to try something new with it here in a few minutes. Okay, so that's the microscope. In fact, let's try something new with it right now. You know, when you're trying to show the superconductor to a big class, normally you show it at the end of the classroom, then let everybody come walk by so they can see it on their way out. I'm going to see if that little microscope camera will focus on it. But I'm missing. Put the nitrogen on the superconductor, let it get cold. While it's getting cold, I get the magnet out, got a little cubic magnet. Let me see.
There you go, you got it.
Yeah. There you go, a little magnet levitating on a superconductor, and everybody in the class can see it for once. And then, of course, it's still fun to walk by it as you leave.
Yeah, it's fun for them to play with the tweezers.
Yes, it's fun for us to play with.
Definitely.
Definitely. Okay, I think that's a success. Yeah, I'm an Explorer, made by Sergeant Walsh in the 1960s. Big, heavy things, very unwieldy. Now we've got a nice set of little coils, various numbers of turns, different kinds of cores, and can be used with an AC power supply, AC voltmeter, and you can verify the transformer relationship pretty easy. I did the Doppler effect, right? Okay. Oh, yes. I should switch over to this DOTCAM now. We're talking about electricity and magnetism at the moment.
You were gonna need Roger guys to be switching all this stuff over for us.
Yeah, when you're getting ready to teach, you got your mind on other things. I'm sorry?
I was just saying, you'll have to run the show at first.
Yeah, it takes a little while to get used to this stuff. Okay, so what I have here are a couple of refrigerator magnets. Okay, and you may have noticed that if you take two magnets like this, you kind of drag one over the other, you can feel some ridges. If you get the orientation right, you can feel the ridges in the way they're made. Okay, so I'm going to take this one and put it down here. This is our old magnetic field viewing film. And you can see, I hope, let me turn the light on here. Is that any better? No. There, can you see the little lines in there? Without that, it's smooth like this. Let me slide this under. Can you see the lines there? Okay. This one's not as good as this one. Let me go in here. There. You can see those ridges?
Kind of leave a little trace.
They leave a little trace, yeah, you can actually do that on purpose. You see that, it leaves that trace? Yeah. Okay, so this is the old-fashioned magnetic field viewing film. Now it comes in color. So the colors change depending on the strength of the magnetic field it's experiencing. And with this, you can still see those ridges, but I think they pop better. Right? And that one's good clean ridges. This one's got some weirdness in the ridges. Okay? And here I have some new magnets for us to play with that are encased in plastic and marked red and black for north and south. And I got 4 of them. And if I lay these down here, I'll put them on the plastic tweezers, get it in the right place. Here's the old viewing film. You can see where the field changes from north to south. And here's the new viewing film.
Oh, yeah. Wow.
Isn't that much prettier? It's certainly worth it. Okay, this is $50. But it's worth the price. There. Okay, so don't lose it, please.
So is it a similar material, different material, the two different materials?
It's got to be a different material. It's basically like liquid crystals,
Right.
little bubbles filled with fluid that have some magnetic thing in them that changes orientation when you put it on there. This has got to be something similar. Yeah.
Like you said,
I first learned about this from Ray Hall on his Physics Fun Instagram.
okay.
So I said, I got to have it. There. All right. Let's go back to the computer and see how those temperatures are doing. They're still rising, and one's still hotter than the other. No surprises, right? No surprises there.
You know, the thing that surprised me is the silver, I thought might not heat up as much as it did. I thought there might be a bigger disparity between the two.
Well, I didn't follow the instructions.
Okay.
The instructions say to put water in.
Right.
I think if I put water in them, we'd be here all day.
You might say, okay.
Yeah. Okay, so now I've got about 15 minutes left. This worked out pretty good with timing. I got our last and biggest finale demonstration right here. I even covered it up. Big reveal.
Huh?
I don't know if you've been watching YouTube or science stuff, but this is something we've been wanting a while. You know what it is? This is going to demonstrate quantum locking. It's a phenomenon of superconductors. What you see here is a track made out of magnets. There's 2 rows of magnets, and they're all clamped in there very tight because they're all facing like the same pole up. And that's really difficult to get them that close together when they're in that orientation. Now, if you don't believe me, I've got this thing called a MagnaProbe that you can come and investigate if you want and see, yes, they're all the same pole up. And then there's this little demonstration platform, but I've got to get something started before we can do any of that. I need more liquid nitrogen. But you put it in the liquid nitrogen and let the liquid nitrogen fill up that gap where the sponge is. Okay? So I'll put that in and I'll put this in. The bigger one actually lasts longer because it holds more liquid nitrogen inside. Give it a second to...
They need to appreciate too, Roger, how hard it is to get the magnets, how hard it was to get all those magnets.
Oh, yeah.
Like that. That was super hard.
Dave and I we couldn't afford this, so we were going to build one.
Right,
And Dave had a great idea how to do it. He had some super glue that worked
right.
for about 3 months.
I remember that.
And then after 3 months, they started
So
popping
you
off.
did purchase that one after all?
This one we did purchase, yes.
Okay.
Okay. So this is quantum locking. You see, I push it on here, and it stays there. Isn't that great fun?
Hey, this is the one we gotta walk by and see now.
You gotta walk up and see
Yeah, we
it.
gotta
That's
walk
why I
by
did
and
this
see
one
it.
last. Okay, now I'm gonna put it on here. That's why they call it locking. Okay, now the magnets here are alternating face up, north, south, north, south. These are all the same face up. But that locks in, and this will not slide on there. You can feel that. Here's one that's a circular field. It'll turn, but it won't fall off. This is a fascinating phenomenon. I leave it to Dr. Ho to explain what's going on, really.
Really?
I just love playing with it. But that quantum locking is something, right? This one's staying nice and cool, too. Let me put it back in there.
It will fall after it gets warm.
It will fall down once it gets warm. I've learned that I need 2 tongs for this.
So is that what the foam material on that disc is to hold in the nitrogen,
Yeah,
to kind of keep it cold?
yeah. Yeah, essentially.
The disc or whatever?
Okay, so now it's locked.
Oh!
I'll just turn it over. And then do this. Oops, didn't get it centered. But there you go. It's locked. It's quantumly locked to that magnetic field. They call it flux pinning, I think. There's a nice explanation that I haven't read. But it's super cool, isn't it?
It is.
Okay. What would you like to see next?
Well, we'll go the other way. Will it spin around the other way?
Will it go the other way? Oh, you bet.
There it goes.
Put one on top.
How will that work? I don't know.
What was
Not
that
gonna
one?
fall on the floor if it warms up too much.
Yeah, it might. Now, there's too much metal there. Just not gonna do that. I better take it down. Oh, it's still pretty strong. Flip that over. Put this here. Now, there it goes. See, it sinks. It sinks when it starts to get warm. And my fingers are starting to get cold. That's it. I didn't invent it. Okay, so I invite you to come up and look around, look at anything that's out, except the liquid nitrogen.